So this is a joint work in progress with George Boxer, who's here, Toby G, who's maybe online, and Frank Calegari, who's probably sleeping, I guess. And but at least the four of us spent some time here together during the trimester. And so what I'm going to present, part of it was done during the trimester. Okay, so let me, so for the benefit of everyone, I will start with an introduction on the modular curve. So let me explain a bit this p-adic Eichler-Shimura theory on the modular curve. Okay, and I mean this is really Pan's theory, although there was some earlier work by Andreatta, Jovita, and Stevens, and also Rodriguez did something in his thesis. Okay, so for the moment, our Shimura datum is the modular curve, and okay, and so I've chosen a prime, and so I pick some level KP inside G of AF, and we have the modular curve SK, which I consider over CP. So the Dirichlet decomposition is the following theorem of Faltings. Okay, and so if you take some positive integer, then you can consider the étale cohomology of SK with coefficient in the sim K of the Tate module. Okay, and so this is a Galois representation. And you tensor with CP, and then this fits in an exact sequence. So here you have the H1 SK bar, so the compactification omega minus K, and then there's a trivial Tate twist. And there you have the H naught SK bar omega K plus 2. Okay, and there's a Tate twist by minus K minus 1. Okay, and so this is a Eichler cross GQP equivalent. All right. So now we would like to take K is minus 1, okay, in this sequence. So I mean on these sides this makes perfect sense, right? So these are current cohomology of weight 1 modular forms, so that's fine. But here obviously it doesn't make sense for the moment because, well, I mean, you can take the C minus 1. Okay, so we have to do something. So let's okay, so let's maybe introduce SKP, which is the perfectoid modular curve. Okay, and so it has a period map to the flag variety, which there is P1, and then it has also maps to the finite level. Okay. Okay, and so there are several sheaves we can consider on this SKP. So we can consider the sheaf of smooth functions. Okay, which is just the colimit of the sheaves of functions that come from finite level. Okay, we can consider the structural sheaf O, which is just the p-adic completion of O smooth. Okay, and so that's the structural sheaf of this perfectoid modular curve. Okay, and then we can also play a similar game with the modular sheaves, and so we can, for instance, consider omega k smooth, which is the colimit as kp tends to 1 of the pkp minus 1 of the omega k at some finite level. All right. So now, I mean, this sequence of Faltings, we can rewrite it like passing to the limit over kp in the following form. So taking limit over kp, we can rewrite this sequence, so in the following form, so the middle guy will become the ohm G, so G is the Lie algebra of G, of the sim K of the standard representation into the H1, so the locally analytic vector of the completed cohomology, so that's the H1 of S Kp, Qp, you take locally analytic vectors, and then you tensor Cp. Okay, so yeah, I'm like implicitly using some control theorem of Emerton, which tells you that this is indeed the limit over the level Kp of the thing both. Okay, and there, well, then you just there have the H1 S bar Kp omega minus K smooth, the trivial twist, and here you have the H naught S Kp bar, bar, so it's a compactification, omega K plus 2 smooth, and here you have to twist by minus K minus 1. Okay. All right. So now, I mean, once you see this, there's like an obvious way to take K is equal to -1, and so it's to replace the Lie algebra cohomology by the B cohomology. So the cohomology of the Lie algebra of the Borel. And so instead you can try to consider ohm B. And now you can just take any character K, okay, so it doesn't have to be an integer. And then valued in the same thing. Yeah, and tensor C. Okay. And so the first thing Pan constructs is a complex. So where here you have some space that I denote by H1W omega minus K smooth. Okay. And yeah, and there I have some space that I denote by H naught identity of well, let me forget the space, omega K plus 2 smooth. Okay, and there's the T twist. Yeah. Okay, and so that's a complex which is again like a cross BQP cross GQP equivariant. Yeah. Okay, so now I have to tell you what are these two guys. Okay, so these two guys are spaces of over-convergent modular forms and higher over-convergent modular forms, which, for instance, I mean, were studied in this higher Coleman theory. Okay, so H. Yep. No, it's a complex. Yeah. Yeah, and K is a character of B, which so K, I mean K could even be in CP. Okay. Yeah. No, but I'll specialize to K is -1 in a second. Sorry. Yeah, the index here is it. I'm going to explain what are these two guys. Okay. So these two guys. Okay. So you have two cohomologies. So there's okay. So first, what's W and identity? So identity and W. This is the Weil group of G. Okay. Okay. So then this Weil group it parameterizes the B orbits on the flag variety. So you have the Brouwer stratification. So P1 is B mod B union B WB mod B. Okay, and so that's maybe A1 and that's infinity. Okay. And so H naught E omega K smooth is H naught of P hot state -1 of infinity omega K smooth. Okay. H1 W omega K smooth. This is H1 with compact support. Hot state -1 of A1 omega K smooth. Okay, And these two local cohomologies, so these are like space of maybe over-convergent modular forms. Okay, or higher over-convergent modular forms. And they can be used to actually compute these classical cohomologies there. Namely, you have a complex, which we like to call the Cousin complex. And so this cohomology is represented by this complex where you put H naught identity omega k smooth. Here you have some differential, which we call the Cousin differential. And here you have H1 omega k smooth. Okay, and this complex, it just comes, from some like obvious like kind of exigency sequence where you have infinity and A1. And so yeah. All right. So okay. So these are the groups appearing there. Okay. And so now what Pan proves is that so let me specialize to k is -1. So if k is -1, then the complex is exact. Okay, so it means that if you put -1 there, then you can put zeros there. Okay, so that's one thing. Okay, but the second thing is that yes, so there is a Galois action. Okay, and so there is a Sen operator there, but when k is -1, the Sen operator is going to be nilpotent, okay, because the Sen operator is trivial on this side, and it's also trivial on this side because k is -1, okay. So you have a nilpotent Sen operator. And so the Sen operator, which is a map maybe let me like abbreviate a bit. Yeah, so the Sen operator, it actually factorizes as a map like this. So you have H naught identity omega 1 smooth, and then H1 omega 1 smooth. Okay, and so you have a factorization like this. So it means that now if you take k to be if you take like the k there to be -1, and so the weight of the modular forms is 1, then you get a Sen map there, okay, and then you also get a Cousin map there, okay, with k is equal to 1, and so the theorem is that the Sen map is the Cousin map, maybe up to a scalar. Okay, so it means that some operator that comes from the geometry, namely the Cousin operator, okay, it comes from the geometry of the modular curve and of the period domain, and some operator that comes from the arithmetic, they actually agree. Okay, and so this has the following corollary. Is that now if you take f in H naught identity omega 1 smooth, which is an eigenform, yes, and if you assume that its Galois representation rho f is irreducible under RAM, okay, which in this case is equivalent to ask that it is Hodge state of weight 0. And this is also equivalent to ask that the Sen operator is 0. Okay, that's the same thing. Then f is classical. Okay, so it's classical. Okay, and I can try to sketch the proof so that you see the main steps. So assume, yep. No, globally. Yeah. Yeah, and the RAM at P. Yeah. Okay, like it's, yeah. So, yeah, so maybe assume F is non-classical. Okay, then it's not hard to see that this implies that the Cousin map on the rho F isotypic part has to be an isomorphism. Okay, otherwise you would get some classical cohomology and then F would be classical. All right, but now if we go back there, so I'm just going to take -1 there. So here I have 1. Here I have 1. Okay. And then I take the rho F isotypic part everywhere. Yeah. Okay. And so here there's an important observation is that this is one-dimensional by the Q expansion principle. And so this is also one-dimensional. But now if you take the rho F isotypic part and you make some dimension count, well, you see that this is one-dimensional. This is one-dimensional. And well, this like can be at most therefore two-dimensional, but it has to be at least two-dimensional because rho F is irreducible. And therefore this is two-dimensional. And therefore, when you take the rho F isotypic part, this is still an exact sequence. But now therefore this equality sen is Cousin, it translates into the equality, it translates into the fact that the sen operator of rho F is non-trivial. Okay, since here the Cousin operator was not trivial, and therefore it means that your representation is not the RAM. Okay, all right. So that was the introduction. No, actually it's not necessary. Okay, so whether the finite slope assumption was necessary, and the answer is no. Yeah, but there can be no. Yeah. Yeah, I mean it's potentially unramified, but it could still. I mean, yeah. Okay. So now we like to generalize this. Okay. So now I'm going to speak more generally about the p-adic Eichler-Shimura theory. Okay, but for this talk, I will focus on GSP4 because this is where we have an application. So for simplicity, let me assume that Gx is GSP4 H2. So this is the Ziegel-Shimura datum. Okay. So well, I will basically use the same notation as before. So I have the Shimura variety that's maybe of infinite level, that's SKP, which maps down to SKP, KP, and then you have the Hochstedt period map to the flag variety, which is now G mod P mu. Okay, and so, well, everything is three-dimensional now. Okay, and so, okay, and also I will ignore compactifications in this talk. So now, what are the weights of modular forms? Well, there are the same things as algebraic representations of the Levy M of P mu. Okay, but this Levy is GL2 cross some GL1 factor that we're going to ignore because I mean this is the center of the group. And so a representation you can write sim Chem1 minus K2 to the standard tensor that K2, where K1 and K2 are in Z, and K1 is bigger than K2. Okay, so that's an irreducible representation of GL2, and so you get some automorphic vector bundle omega K1 K2. At each finite level, and they're equivalent. All right. So now our interest for GSP4 and Siegel modular forms, it comes from the following conjecture. So if you take A over Q be an abelian surface with trivial endomorphisms over Q, then there exists level K and cohomology classes C0 in H naught, maybe SK, omega 2 to C1 in H1, SK omega 2 to C2 in H2 of SK omega 1 1 and C3 in H3 of SK omega 1 1. And there are eigenclasses. And we have that the L series of these classes is the L series of the abelian variety. Okay, so, well, in slightly more modern language, so I mean, yeah. Well, maybe one way to think about this is that there should exist some pi f, which is a smooth admissible representation of GAF, irreducible, such that there are two automorphic forms on GSP4. So pi infinity G for generic tensor pi f, and pi infinity H tensor pi f, where H is for holomorphic. Okay, so these are automorphic on GSP4, and sorry, I need some chalk. And yeah, pi infinity G, pi infinity H, there are limits of discrete series. And maybe the classes C1 and C2, they correspond to this automorphic form. And the classes C0 and C3, they correspond to this automorphic form. Okay. Okay. And well, in general, there's not even a unique choice of pi f, but there's a better choice, which is to take pi f to be generic at all finite places. And if you make this choice, then actually you can kind of pin down a rather canonical C0. Okay, and that's called the paramodular conjecture by Brummer and Kramer. Okay, anyway. All right, so okay, so we want to study this. So here's the first theorem. So we're going to consider the X minus 1 B on completed cohomology take locally analytic vectors and tensor with CP. Okay. that's maybe a bit too hard to understand completely. So we also do some localization. We take the ordinary part and we take the non-Eisenstein part. So this means ordinary and then non-Eisenstein. Okay? So we consider this. And so the first theorem is that this is concentrated in degree 3. Okay? So that's the middle degree there. And moreover, there is a filtration. With graded. So you have the H3, W3 of omega 1, 1 smooth, ordinary, non-Eisenstein. The H2, omega 2, omega 1, 1 smooth, ordinary, non-Eisenstein. The H1, omega 1 of omega 2, 2 smooth, ordinary, non-Eisenstein. And the H0 identity, omega 2, 2 smooth, ordinary, and non-Eisenstein. Okay, so now I have to tell you what are these graded species, but these are spaces of higher over convergent modular forms that are studied in higher Coleman theory. So the definition is quite easy and similar to what you do in the modular form case. So, but let me just explain this. So you, okay, so again, we have the Brouwer stratification. So the flag variety, sorry, first I should say that this set of W3, W2, W1 identity, this is what's often denoted by MW. So this is the set of costant representative for the cosets W divided by WM, the Weil group divided by the Weil group of the Levy of P mu. And this parameterizes the Brouwer stratification on the flag variety. So namely, the flag variety is the union over W in MW of the orbits PWB mod P. Okay, all right. And so now what's the definition of this W cohomology? Well, with value in some sheaf. Maybe let me write K1, K2. Smooth. This is just the local cohomology of omega K1, K2 smooth over pi hot state minus 1 of the corresponding strata. Okay. So I'm maybe a little bit vague there about the definition, but it means that you have some support in some directions, some partial support set. But well, I could be precise, but I think anyway the case of modular curve already gives some intuition. Okay, so you have these local cohomologies, and again these local cohomologies, they can be used to compute the spaces of classical modular forms. So let me give some example, and the example which is of interest to us is that, so for instance, if you consider the space of classical weight 2 modular form, yeah. It's non-Eisenstein. Okay, so it means that yeah, I want to kill the cohomology of the boundary. Yeah. Oh yeah, so sure, sorry. Okay.
What notation do you use for your percentage? W and the subscript?
Oh, it's W3, W2, W1, and then there's always the problem whether the identity should be called W0. So huh? This is MW. Yeah, sorry, this is MW. And then you have it's WM modulo W. Yeah, so sorry if my writing is not very good.
That is the definition of non-Eisenstein.
Well, I guess that just the representation is not valued in a Levy. Sorry, in a parabolic. Yeah, that's enough. Yeah.
So then some work has to occur to prove that such things can't occur in a boundary.
Yeah, but yeah, exactly. Yeah. Okay, I can tell you after. So, okay, so for instance, that's the classical cohomology in weight 2, okay? But I take the ordinary part and the non-Eisenstein part, and this is actually represented by a complex of amplitude 2 of these overconvergent modular forms. So namely, this is represented by this complex. Yeah. Okay, and so that's again what we call a Cousin complex, and this differential, let's call it Cousin. Okay, and then the same thing holds true for the cohomology of omega 1 smooth. If you take the ordinary part and the non-Eisenstein part, except that now it's a complex which is in degree 2 and 3, and you have the H2W2, and then you have some Cousin map, and you have the H1. Sorry, the H3W3. Okay. Yeah. So I mean, there's a parallel story. Okay. All right. So now, I mean, unsurprisingly, our second theorem is that the Cousin map and the Sen map agree. So the second theorem is that the Cousin map agree with the Sen map. So let me be a bit precise. So there, okay, I didn't put the twist, okay, so I'm sorry, but maybe here are the weights. So these two guys have weight 0, and these two guys have weight -1, okay? And so the Sen operator is unipotent, sorry, is nilpotent on this part, okay? And it's well, it's unipotent on this part actually, okay? And so you get, and so using the Sen operator, you indeed get two maps. So you indeed get a map between, let's say, like Sen +1 gives you a map. No, maybe Sen -1 gives you a map from H0 identity to H1 W1, and the Sen operator gives you a map from H2 W2 to H3 W3. Okay, and so this map that come from arithmetic, they also agree with the maps that come from geometry from there. Okay, okay. I mean, just as before. So now this has a corollary, which is some classicality theorem for these overconvergent modular forms. So for instance, if you take F, which is in H0 identity W2 to smooth, okay, so I take the ordinary part, the non-Eisenstein part, okay, and now I'm going to make a couple of assumptions. So I'm going to assume that rho F has large image. Okay. So let me not be extremely precise about this. So the key assumption is that rho F restricted to GQP is the RAM and is P distinguished and it's pure. Okay, so the RAM assumption is quite natural if you want to. I mean, sorry, let me write the conclusion. F is classical. Okay, so the only like very natural assumption is that rho f restricted to GQP is the RAM. Okay, and then we have a couple of extra hypotheses. So the hypothesis of being P distinguished and pure, these are hypotheses which implies that the local deformation ring is smooth at rho f restricted to GQP, and so this will be used in the proof. And again, the assumption that rho f has large image, this is kind of a Taylor-Wise assumption. Okay, and maybe so I can like say some words about the proof. So the proof is like, I mean, this is as in the modular curve case. The modular curve case, except you need multiplicity 1. Okay, so in the modular curve case, the multiplicity 1 came from Q expansion, but here it's not free. I mean, so how do we prove multiplicity 1? We construct a Taylor-Wise system, and then we use some smoothness of the local deformation ring to deduce that let's say the modules of modular forms are free over the Eichler algebra, and then we can compute the rank at some maybe automorphic point, and then we can use automorphic argument to see that the rank is 1. Okay, I should say that also the construction of the Taylor-Wise system requires some integral structure on these over convergent cohomologies, which is provided by Eichler theorem. Okay, so sorry, that's a bit sketchy, but yeah, but that's like as in the modular curve case, except that you need to struggle with this multiplicity 1. Okay, so maybe I would like to say just one word about the proof of the theorems. So maybe I say one word about the proof of this theorem. Okay. No, I will. I mean, yeah, and then the application will be to the conjecture. Okay. So far, I'm just explaining some things about Siegel modular forms and Siegel over convergent modular forms, and then I've proved something that maybe looks relevant, namely that we have a technique to prove that an over convergent Siegel modular form is actually a classical modular form. And then our plan will be to show that certain abelian surface is actually attached to such a guy, over convergent, and then deduce that this guy was actually classical. Yeah, that's where we are going. Okay, so yeah, let me say briefly something about the proof of the theorem. So the proof of the theorem. So in the theorem, you want to compute some x1, sorry, x minus 1 minus 1 in this completed cohomology, locally analytic vector. So the first step is to relate this to coherent cohomology. And so this is something we actually already saw in Pan's talk. And so, yeah, and so this is a combination of the primitive comparison theorem of Scholz, and some work of Pan and Rodriguez on locally analytic vectors. Okay. Okay, so that's the first step. Then you want to take the XB. Yeah, and so you actually compute the B cohomology at the level of the sheaf. Okay. Okay, and so now you want to compute this. So the idea is to use the Brouwer stratification. So actually we're going to compute this on each Brouwer strata. Yeah. And so the claim is that this is a sheaf of over-convergent modular forms. Okay. And let me just develop a bit on this. So if you remember a weight of a modular form, this is some finite dimensional representation of M, the levy of P mu. Okay? But, well, let me do something. Let me, instead of using M, I'm going to use MW, and MW is W minus 1 MW. Okay? Because, yeah, actually I'm choosing the base point W on the flag variety, and therefore the stabilizer or the levy of the stabilizer of this point W is actually this conjugate levy, and so it's better that I use this. But anyway, the representations are the same. The groups are conjugated. So now what's the weight of an over-convergent modular form? Then this is actually an object of category O, where this is category O for matrix MW, which is the Lie algebra of MW. Okay? So that's like the natural way to think about things. And so now I can tell you actually what is this sheaf of over-convergent modular form, this XB OLA. And so actually what we prove is that this XB minus 1 OLA, this corresponds to the following complex in category O. And so this complex is the cohomology of some unipotent radical of PW acting on the Verma module for the big group. Okay, so PW is W minus 1 P mu W. PW is its Lie algebra, okay, with levy MW, and the unipotent radical is UPW. Okay, and so this is a Verma module for the big group, and so you take UPW cohomology, and so you get some complex in category O, whose amplitude actually you can compute, and is 3 minus the length of W3. Okay. Yep. Yeah, thanks a lot. Okay, and so you need to analyze this. Okay, and so in there you have kind of the major contribution. So the major contribution is some Verma module, which is UMW tensor U BMW of some twisted action by W on the weight -1, Okay, so that's kind of the main contribution. That's kind of the main contribution. And I won't say that this main contribution was identified by Juan Esteban in his thesis. Okay, but okay, and this is the weight. This is the weight that you see. That you see in the classical hot-state decomposition. Okay, so that part is completely aligned with the classical hot-state decomposition. In general, there will be other contribution, like this cohomology is more complicated. But the remaining part is non-ordinary. Okay, so I believe that the remaining part is quite interesting. For example, if you want to study triangulations and critical triangulations of Galois representations, and yeah, I mean, it's clearly very interesting, but here we're doing ordinary things. And so if you take the ordinary part, you kind of kill the rest of the contribution. And this is why you arrive to such a simple answer, which is given up there. Okay, so you really have cohomologies in degree 3, and you have this nice filtration where actually the weights are exactly the weights you see in the classical hot-state decomposition. Okay. Okay, and I also want to say that probably this has nothing to do special with GSP4, and yeah, and we hope we can set up the theory for the general group. Yeah.
Weight doesn't have to be -1.
No, exactly. Yeah, I mean, it just has to be what's called p-adic Cayley non-Liouville. Okay, I mean, there are some weird p-adic numbers which are. Yeah. Okay, I mean, I could. Okay, but now it's really time to turn to applications. Okay, so yeah, sorry. So I won't say more. Yeah, yeah. Okay. So. Okay, so now applications. Okay, so let me begin with some crucial observation. Is that SP4 of F2 is S6, and inside S6 you have S5, which is the stabilizer of a point on the permutation representation. Okay, now about genus 2 curve. So a genus 2 curve, C over Q, say, as an equation. Y squared is f of x, where the degree of f is equal to 6. We say that a genus 2 curve has a rational Weierstrass point if f of x has a Q root. Okay, and so in that case, you can find a lower degree equation for your genus 2 curve. Namely, in that case, C over Q has an order equation. Y squared is g of x, where the degree of g is 5. Okay, so you do some change of variable that sends the Q root of f of x to infinity. Okay, and that way you reduce the degree of the equation by 1. Okay, and maybe it's also useful to know that any simple, principally polarized abelian surface is a Jacobian. Okay, so now So now let's start with the first modularity theorem. So the first theorem is this one. So you take A, which is the Jacobian of a curve y squared is f of x, where the degree of f is 5. Okay, so it's a genus 2 curve with a rational Weierstrass point. And so you assume that. So first, you look at the two torsion representation of GQ, and this will actually automatically be inside S5. This is by the Weierstrass point. Okay, this forces the image of Galois to land in S5, but you assume that it contains A5. The second thing you assume is that A has good ordinary reduction at 2, and is 2 distinguished. Okay, and finally, you assume some kind of oddness condition, mod 2, which is that f of x has only one root in R. Okay, and so that's kind of oddness mod 2. Yeah, and then the conclusion is that A is modular. All right, so how does the proof go? So for the proof, I'm going to assume that rho A2 of GQ is F5 for simplicity. Okay, otherwise you need more arguments. And okay, and so the idea is to use the Artin conjecture for GL2. So you have okay, so you have GQ that goes to F5, and then F5 has a two-dimensional representation over Z bar. Okay, but you can take the sim cube of this representation and you land into GSP4 of Z bar, and then you can reduce mod 2 and you arrive in GSP4 of F2 bar. Okay, so this kind of bottom arrow is our Galois representation rho A2 on the two torsion of A. And this top arrow is some Artin representation for GL2. Okay? And so we know that rho prime is rho F, where F is a weight 1 modular form. Okay? But then this implies that rho A2 is rho of the sim cube of F mod 2, where the sim cube of F is automorphic on GSP4. So that's a case of the symmetric cube functoriality that we saw in James-Stokes, except that this is a low-dimensional case, and so this was already proved by Kim and Shahidi. Okay. Now, I mean, there's a slight problem with sim cube of F. It is that it's very irregular. Okay, it's not cohomological. It's very regular. But this can be fixed easily because you can pick G, which is congruent to F mod 2, and which is ordinary at 2. Okay, I mean, F is ordinary, so you put it in a Hidalgo family, and then this is also rho of the sim cube of G mod 2. But now the sim cube of G is a cohomological representation on GSP4. Okay, and so this is good, you see it in the cohomology. Okay, so then you can apply your modular lifting theorem. And so you did use that rho of A to infinity is rho of F, where F is in H0 identity omega 2 to smooth. Okay. So here you applied a modular lifting theorem in the unrestricted C situation somehow. It means that you apply it with, like, sorry, in the unobstructed C situation. So you apply it with kind of p-adic modular forms. Okay, and then okay, and so that's, I mean, that's okay. I mean, that's kind of a bit standard in the theory, I would say. I mean, except maybe it's a bit tricky because it's mod 2, so you have to be a bit careful. I mean, it requires work, but it's and then you deduce now by the classicity theorem, because this guy is obviously the RAM at 2, and so this implies that F is classic. Okay. So yeah. Okay. So I think, I mean, yeah, I have more things to say, but let me just make some remarks. So the first remark is that it's about yeah, like in history, like I don't like it's interesting to see that Artin representation were used to prove modularity of elliptic curves, which were then used to prove, but the solvable ones, and then modularity of elliptic curve was used to prove the Artin representation, the Artin conjecture for in the icosahedral case, A5 case, and then again using icosahedral to do something with abelian surface. So there's a kind of ping pong game. All right, and also yeah, I should say that also here there's really a difficulty, which is that the sim cube of G, it has weight 3, and not 2, 2. Okay, so like in our previous work, we proved some modularity lifting theorem where actually you add a congruence with a modular form of the weight, but where the weight was already good. The weight was 2, 2. But here there's kind of a change of weight in the story. Okay, and that's why we need all these new arguments. Yeah. Okay, so now we do a 2-3 switch to get more modularity. Yeah, so now we do some 2 switch, and so here is the theorem. So you take A over K, Q, an abelian surface. Okay, and so well, there are like kind of some obvious assumptions. So the first assumption is that the image of Galois on the 3 torsion should be big. Okay, that's kind of a big image assumption. Then we need to assume that A has good ordinary reduction. At 3, and is 3 distinguished. Yeah. So that's also like really an important assumption. And then we're going to make some assumption at 2. And so the assumption at 2 will be that rho A3 restricted to GQ2 isn't ramified. And rho A3 of FROB2 belongs to some explicit list of conjugacy classes. Yeah, and then the conclusion is that A is modular. Okay, so let me maybe just explain briefly why we have this assumption, the second assumption. So the proof, so the idea is to find some B over Q, where B of 3 is A of 3. And well, clearly B, but first theorem applies to B. Okay, so in particular, B over Q2 has good ordinary reduction. Okay, but B over Q2 having good ordinary reduction clearly places restriction on what its Frobenius set to. And so you want that but on the other hand, the Frobenius set to mod 3 is prescribed by rho H3, and so you want some kind of, and so you just, and so there has to be some condition, right? That somehow this should be in some conjugacy class which has a chance to arise as the reduction of an ordinary at 2 Frob 2. Okay, and let me. Okay, so the way we find this B is because there is a moduli space of principally polarized abelian variety with level structure at 2 and 3, which is rational. Okay, that's kind of an accident of nature, and so it has lots of rational points, and so you can cook up a B that way. And let me just finish by some example in which our theorem applies, and that's simple. So if you take C, which has equation y squared is f of x, where the degree of f is equal to 5, okay, and you assume that rho of the Jacobian of C at 3, is GSP4 of F3. Okay, so that's kind of a generic condition on the monodromy mod 3. And you assume that C has good ordinary reduction at 2 and 3. As good ordinary reduction at 2 and 3. Then C is modular. Okay, and so yeah, and well, it takes some computer check to see that actually such a C immediately, the Jacobian of such a C automatically fulfills this hypothesis. Okay, so yeah, I'm going to stop here. Thanks.
Is it easy to check the symmetry of the equation? In this condition, like the kind of like the image of rho is the least obvious thing, I guess.
Yeah. Well, but you need to reduce modulo various primes and find lots. No, so I don't see. Yeah, no, I don't think this. I don't know if it. Yeah, we have explicit examples of equations. Yeah, but for in some sense that's 100%. Okay, this condition and these two conditions are really imposing a restriction on the reduction mod 2 and 3 of this f of x. But there's like a finite list of possibility for f of x mod 2 and 3, and then you just have to land in the right congruence class. So in some sense, yeah, that's applicable, concrete. Yeah. Yes.
Also considers the case when the weight is not equal to 1.
Yeah.
And it's kind of easier, right? To show that.
It's well, yeah. To show what that it,
modular and run implies modular.
Yeah.
Can you do this in this context?
Maybe in some future. Yeah. So here so you're right. So in the modular curve case, there's really a distinction between the weight 1 case, which is totally irregular, and the higher weight case where the H-state weight are distinct. Okay. In this case, we have a kind of a mixed situation, right? Because the weights are 0, 0, 1, 1. So, but by imposing the ordinary condition, is a way to pretend like we are just like dealing with weight 1 forms, and therefore we don't have to deal with the theorem part of the story, I guess. Like maybe, okay, a better way to say it is that in the ordinary case, being H-state is the same thing as being classic theorem. Yeah. Whereas if you're not ordinary, then it's what I just said is not true. Okay, and so you need to. So maybe we'll have to mix both techniques. Yeah. Yes.
Do you see any hope of using more primes beyond 2 and 3 and pushing and weakening hypotheses that way? Can you do a 3-prime switch?
I don't think so, but that's not my specialty. But I think it's very rare that moduli space of abelian surfaces with level structure are rational. And I guess, I mean, maybe George has some ideas, but I think if you go to the prime 5, like if you put some 5-level structure, then you're screwed. Yeah, maybe some intermediate level structure that could be investigated. Yes, but maybe base change is the best way to relieve the hypothesis. Yeah, so solvable base change. Yeah. Yes, please. Where do we use Eichler theory?
Yeah, and for modularity, I think you still need like arithmetic in a very essential way to.
So I guess, well, yeah, I mean, okay, yeah. So I think it's been used in 2 places there. So first, it's been used in when I claimed that when I took the ordinary part of this x minus 1 minus of this xb minus 1 of completed cohomology, this was only in degree 3. And so yeah, I guess that there I've implicitly used Eichler theory, which gives me some lattices and some bounds for the slopes on these over-convergent cohomologies, some optimal bounds. So it was, I guess, used implicitly there. And then it was also used in the proof that you have of the multiplicity 1, except that probably in this case you could just be done with classical Ida theory, because maybe you just need to prove it for the H naught. So maybe classical Ida theory would be enough in that case, yeah, for this part of the story, yeah.